Hello, this little video is about the splitting fields of polynomials over the rationals. Let's take an irreducible polynomial with rational coefficients. Let's also assume that it is monic. And define the splitting field of that polynomial to be the result of attaching all roots, complex roots, of this polynomial to the field of rational numbers. So this is the splitting field. Of the polynomial p, simply because using these new numbers, combinations of rational numbers and the roots, we can factor p into the product of linear terms we just attach to the rational numbers, the minimal number of numbers, the minimal amount of numbers which would allow us to do that. So the fact which is going to be checked independently is that any splitting field is Galois. Is a Galois extension of the rationals, which by the definition is to say that they have the maximal possible amount of symmetries. The number of symmetries of the order of the automorphism group will be equal to the degree of the extension. So let's look at an example of all that, of the rationals. We'll construct the splitting field of this irreducible polynomial. The procedure is straightforward. We just need to start with the collection of roots of this polynomial and attach them to rational numbers and see what happens. So to see what the roots are is the first step. And the roots are really they are products of the real root, which we call the cubic root of 2, and some root of complex root of 1 of degree 3. This is the set of all of them. And that is simply because if we do have two different roots, so a cubed and b cubed are both roots of this polynomial, so cubed they are equal to 2. Then taking a ratio a over b, we will inevitably get one of those roots of degree 3 because it is raised to the power 3 will be equal to the ratio of two things which are 2, so it will be equal to 1. So any pair of roots differ by some complex root of 1 of degree 3, and hence we have the complete description of roots of this polynomial. We have exactly 3 of them labeled by the roots of 3 roots of degree 3 of 1. So when we are constructing this splitting field, where really it's enough to attach this real number, the cubic root of 2, or maybe I'll just write it like that, and attach all these 3. But we know that we don't have to attach them all separately. It's enough to take one of them, any non-trivial, say epsilon 1, which is e to the 2 pi. I over 3 will be good. We attach it square, so we attach all the interesting roots. So that is really the two-stage extension of rational numbers, which gives us our splitting field. The next step in analyzing an extension is to see what is its degree. So we have to figure out how many linearly independent over the rationals elements does this field extension have. And this two-stage presentation, or rather two-stage presentations of this, would be beneficial. So we can look at, again, the splitting field is the result of attaching just two numbers, this real cubic root of 2 and this complex root of 1, and then we could write it as a two-stage extension of the rationals, first attaching the cubic root of 2, and then attaching this complex root of 1. Or the other way around, we could start with attaching the complex root of 1, have the cyclotomic extension of the rationals, and then attach to it the cubic root of 2, this real number. So we computed the degree here, it is 2. We computed the degree here, it is 3. And then we know that, we attach to this field, we attach, say at this leg, we attach a complex root of 1. So the degree has to be not larger than 2, will be divisor of 2. So the degree, whatever it is, divides 2. And here the same argument we already have, the complex root of 1, we attach the cubic root of 2 to the result, and the cubic root of 2 over the rationals has degree 3. So again, the divisor of 3 is the answer here, whatever it is. So all in all, the degree should not be larger than 6. Multiplicatively, it should be divisor of 6. But at the same time, it is divisible by 2 and by 3, because these guys sit inside. So this decomposition should be given a degree, which is the product of 2 and something. This decomposition should be given a degree as a product of 3 and something, so it must be 6. So this is really degree 2 extension, and this is really degree 3 extension, and the whole degree is 6. And that is not surprising. So splitting fields, if they happen to be so what I'm going to say is applicable to specifically to degree 3 extension, so to degree 3 polynomials. So splitting fields of a polynomial with degree 3 can be either of degree 6 or degree 3. There is nothing else it can be. So we're seeing the case of degree 6. So that is a Galois, again by the generic fact, and that means that the Galois group, the automorphism group of this extension, has to be the largest possible, the S3. So let's see how it comes about in this concrete example. Let's forget about generic notion and see how really the symmetries of this extension are organized. So let's start with one of those symmetries, and any such symmetry for any splitting field is completely determined by what it does to the roots we attach, by what it does to these roots. And we can separate what it does to this cubic root of 2 separately, and what it does to one of those epsilons, say epsilon 1. It's not really a root of our original polynomial here, but it is a number which we effectively attach, and any symmetry will have to move it somewhere. So let's see where it can move it. Well, this number satisfies the equation t cubed minus 1 equals 0. So any image of this number under any automorphism has to satisfy the same equation. So that has to be some other root of degree 3, complex root, and we know how to get them. We just have to raise our given one by some power, into some power. So k here has to be, well, effectively number mod 3, but it has to be a non-zero number, an inversible number, because we want to have an automorphism, we want to be able to go back. So for this number, the image under some automorphism has to also satisfy the same polynomial equation as this is satisfied by, and the polynomial equation is the number cubed is equal to 2. So we have to see, as a result of applying an automorphism, we have to see one of those roots. So it should be some epsilon, which is a power of epsilon first, times the cubic root of 2. So now this power is the second controlling label of our automorphism, second piece of data which really gives out our automorphism completely. Because if we know if we know automorphism on these two numbers, we know it everywhere. So any automorphism has to have this shape, and K and L will determine it completely. So L, this power of the root here, can be anything mod 3 really. It can be 1, so we'll just be fixing this cubic root of 2 as a real number. Or it could be any other power, like, could be 0, sorry, it could be 1, or it could be 2. So let me write now my phi, since it is controlled completely by these two numbers, let me write it with these labels L first and then K. And now I know my Galois group, which wants to be S3. I know it as a group of automorphisms labeled by pairs of numbers. I have two possibilities for K, either 1 or -1 or 1 or 2, and 3 possibilities for L. The total number of possibilities is 6, total match with the order. Let us see the group structure in this way of writing our automorphisms. So what we're after is the formula for the composition. So I'm composing one of those phis with labels L and K with some other element of my symmetry group, and the labels will be like S and R. So I want to see what is the result. It has to be one of those symmetries again, so it has to be phi with some labels. So I just need to compute what these labels are, and I know how to. So the second label will be what happens under this symmetry, under this combined symmetry with epsilon 1. So I just need to compute what happens after I do these two transformations together on epsilon 1. And the first one simply raises it to the power R. And the second, by the very definition, supposed to raise epsilon 1 to the power L, and then it is all to be raised to the power R. So the, sorry, not L, but K. So the total effect is the product of K and R. It's more interesting to run computation on this second generator of my field on the cubic root of 2. But it's basically the same technique. So first we applied our first automorphism, and that is the recipe for it. So the result will be still cubic root of 2 shifted by the power of our epsilon 1, and the power will be this S power. And then we have to see separately what the second automorphism does to each of those factors, or maybe even put in the S power outside of the second automorphism. And then we know what to do. So this guy is raised to the power K. So the combined effect is Ks. This is just epsilon to the L, epsilon first, times the real cubic root of 2. And the total epsilon effect is K times S plus L. So reading these two answers, so repackaging them into the indices for the composition will be now straightforward. That is the first index, it's Ks plus L, and the second is K times R. So we could see that in the second coordinate of our two coordinate labels, we just multiply. That's the group structure in the second coordinate. In the first coordinate, we multiply K with S, and then we add it with L. So that is what is called the semi-direct product. Technically, it is the literally the rule for the semi-direct product of integers mod 3 invertible, acting by multiplication, this term, on integers mod 3 under additive. So that is a semi-direct product. That is a non-abelian group of order 3 6, and that has to be isomorphic to S3. So we just recovered the group of symmetries of our splitting field, the group of automorphisms which in effect permute in the S3 permutation way all our 3 roots. But we recovered them in this algebraic way, in the way we saw our extension as iterated extension. We recovered it using this computation. So that's it for this short introduction to splitting fields. More to come. See you later.